In the previous video, we discussed count vectors, and in particular how count vectors give you robustness against spelling errors. In this video, I would like to continue that train of thought, but I want to explore how you might get spelling error robustness in embeddings instead. And to demonstrate this, I'll be using the English Core Web Medium language from the spaCy package, and I'll be using the English fasttext embeddings. And we'll just have a look at how these word embeddings behave differently, and then we'll explain why. So what I can do is I can ask the spaCy language for tokens that are very similar, as far as embeddings go, to the token university. And spaCy tells me that university is similar to college, colleges, campus. So far so good. And I can do the same thing with fasttext. University, college, I would argue that the results are similar here. But let's see what happens when I introduce a spelling error. And what I'm going to do is I'm going to spell universities with a C instead of an S. And let's see what happens with spaCy and fasttext in this case. And we see that spaCy is having a bit of trouble identifying which words are similar, while fasttext is actually doing quite well. And the reason for this is that as far as spaCy goes, universities is an unknown token, and that will get mapped to a 0 vector, but fasttext doesn't do that. And if we wanted to explain where this comes from, you could say that maybe this fasttext language is trained on a bigger data set that actually has some of these spelling mistakes, and that could be an explanation. But fasttext also has internals that make it more robust against spelling errors in general. And it's actually quite a cool trick, so I figured it'd be good to spend a video explaining how that works. Typically, the way that a word embedding is generated is that you have a token, and I'll just take cities as an example. But typically what you would have is you'd have a token like cities map to some numeric array. Some floating point numbers in here. And this is of some dimensionality k. Typically k is big, something like 300. But the idea is that you have a mapping from a token to something numeric that represents the meaning of that token. And notice, to be explicit in this case, I've written down the form with these brackets before and after, mainly to indicate the beginning as well as the end of the token. Now, let's consider the count vectorizer trick that we discussed in the previous video. What we can do is we can say, well, that original token, that consists out of subtokens. And let's take the subtokens with the n-gram trick. And let's say that we have an n-gram of size 4. Then this token over here can be split up into these subtokens. We have CIT with the start token, CITI, ITIE, TIES, as well as IES close token. And if we look at these specific subtokens of the original word, I would like to make one observation as far as meaning goes, because these subtokens typically occur in more than one word. If I have a look at this one would occur in city, as well as cities. And it's clear that those two words have an overlap in meaning. And the same thing for this subtoken. This one occurs in cities, as well as, let's say, the word policies. And again, we see some resemblance in meaning. The ending of a token with IES in the English language typically indicates plural, that there's more than one instance of it. And we see a very similar thing happening again with the first subtoken as well. So considering that these subtokens actually have meaning, how about that we train embeddings for the subtokens instead? We can take each subtoken and then perhaps map that to an array. And each of these arrays, of course, will be different. But one thing that's now nice is that we can say, well, we don't take the original token and then map that onto a vector. But instead what we can do is we can say, you know what, take all of these subtokens that we've trained for, and then just add them together to get to our final representation for the word cities. And by doing this, we actually get a couple of interesting properties as far as word embeddings go. For starters, I hope that we still recognize that even if you add all these subtokens together, that there's still a unique mapping from the final array that we end up with to the token that we're interested in. So we still have that convenient mapping property, but in practice, there's also two other interesting properties that are very useful when you're doing this. Let's now, for example, say that I misspelled the word cities. And let's say that I misspell it because I introduce a Z over here. And let's now also assume that we never saw that token in our training data. Then we still have some overlap with subtokens that we've seen before. For example, this subtoken is still captured, so is this one, as well as this one. It's just these two that we don't map. And if we then want to know a numeric representation for a token that we've in general not seen because of a spelling error, then we can still take this subset of subtokens, add all of those together, and then that still gives us an array that still has some meaning. And this gives us the opportunity to take our unseen token and then still map that to something that is not an array of zeros. We may still be able to capture some meaning by doing this. But it's not just for spelling errors where this is going to be very, very useful. What I have now done is I've written down a couple of words, and I'm just going to discuss the language phenomenon with these words. So one of the things that I can observe with all of these words is that the prefix, the beginning of the word here, they all have rather specific meaning. And if I have subtokens, then I might be able to capture what that means. Astro, that has something to do about the stars. Geo, that probably has something to do with the Earth. Similarly, you can also imagine that metry, that has to do with measuring something. And we also have this ology that we can learn the meaning from. And let's say that I've captured the meaning for all of these prefixes as well as for all of these suffixes. But this happened in a dataset that did not have the word geometry. Well, because we've learned the meaning of the prefix, we could plausibly assume that, we've got this geo part covered. That's because we've learned the meaning of that here, and I can use a similar argument to argue that we've got this metry over here covered. Odds are we've seen many examples of tokens that end with metry in our dataset, even though we've not maybe specifically seen geometry. And this is a nice observation, because we can still suggest meaning for unknown tokens in general. If you think about it, spelling errors are a special case of this phenomenon, this out-of-vocabulary phenomenon. And this way of handling is relatively effective. Even when you train on Wikipedia, you may not have access to all the words that people may use in real life. Now, this effect of combining words together to create a new token, that's not something that just happens in English. In fact, many European languages have this phenomenon. For example, in Dutch, we have the word schildpad, which literally means shield toad. Schildpad, by the way, means turtle. And you can imagine that if you look at a turtle, it's like a toad, but one with a shield. And of course, the translation here is not perfect, but again, we have some robustness against an out-of-vocabulary word, because the language is usually built up of these morphological features, so to say. So I hope that you would agree that, in general, it will be nice if we are able to train embeddings that also take these subwords into account. Knowing that fasttext is doing this, let's now wrap up this video by just looking back at the results that we started with, because there are some interesting lessons to learn from that particular example. Now, let's look back at what fasttext does. We give it universities, which is spelled with a C. But let's look at what it gives us back. It says university, universities, which is all good. But notice how it also gives us places. And places has not a whole lot to do with a university. And you could argue the same thing with countries over here. So it seems like the context of another word is somehow mixed in because of this spelling error. And if you then have a look at what word is mixed in here, it's the word cities. So in this case, it is still decently able to recover from the spelling error, but we also see that the meaning of the word university, because of this particular spelling error, is somewhat blended with the meaning of the word city. So we see that we do get some robustness, and by and large, looking at this, I would argue that we're still much closer to the idea of being a university than being a city, but we should remind ourselves here that no word embedding is perfect. Yes, we get some robustness against spelling errors, but we are also morphing the meaning of the word here a little bit, and that is something that you just want to be a little bit aware of. Another thing that I also briefly want to mention here is the way that spaCy handles unknown tokens is of course fair. spaCy is meant as a natural language processing tool for general texts, and if there's a word embedding that you aren't really sure what it means, then setting the embedding values to 0 is a nice way to at least prevent wrong assumptions from seeping in. And I hope that this example does demonstrate that that is a risk to at least be slightly aware of. spaCy is designed to be a tool that is production ready. Fasttext originally had a different concern, to be state-of-the-art at a task in a more academic setting. It's fair to observe that both word embeddings are different in behavior here, because they are both designed toward a different use case. spaCy internally does some tricks to keep the memory small, and this includes mapping similar tokens in a vocabulary to the same numeric representation. This also brings us to a downside of fast text embeddings. Depending on the language model that you pick and download, it can take between 6 and 7 gigabytes on disk, while the spaCy model that we've chosen only takes about 115 megabytes. So you could say that fast text indeed is perhaps more expressive, but it comes at a cost, both in disk as well as some assumptions that it's making here.